A is, will a reaction happen? How do we decide without doing the reaction whether it will happen or not? Okay. Well, we've already looked at one of the pieces that'll help decide whether a reaction will happen. Okay. And whether it will happen is completely separate from how fast it's going to happen. Okay. So, and the way that energy decides whether something's going to happen is pretty simple. An example that brings to mind is, why don't you store a bowling ball on the top shelf? Because eventually that bowling ball is going to end up on the ground, right? Okay? Because it's got higher energy up there, it's going to get to lower energy. And if your toe's in the way, you're going to pay a price. Okay? So that is how energy decides whether reactions happen. Things that release energy tend to happen. Things you start off with high energy, end up with low energy, they tend to happen. So if I start off with high energy and end up with low energy, I have to give that energy away. So one of the things that helps predict whether a reaction is going to happen is whether it's endo or exothermic. Reactions that happen tend to be exothermic. So exothermic reactions tend to happen. But it's not enough. Okay? Energy by itself doesn't explain everything. Because it doesn't explain something as simple as ice melting. In order to get ice to melt, you have to put heat in. But if I put an ice cube on the counter here, it's going to melt. It will happen. So it can't be the energy that's making it happen. It can't, because it's downhill. It's not. It's like it automatically goes up on the shelf by itself. And that doesn't happen. Okay. So an ice cube has to absorb heat to melt, but it melts anyway. I've got to put heat into the ice cube to get it to melt. But if I just put the ice cube on the counter, it's going to melt. Why does it happen? What makes it happen? So there's a second factor that affects whether reactions happen or not. And that is entropy. Entropy. I wish it was hugely different than enthalpy, but it's not in terms of words. Entropy. Okay, if you look up entropy, they're going to say that this is what entropy is. Okay? The degree of randomness or disorder. How disordered it is. Things that have high disorder have high entropy. But I'm going to tell you, that's not actually the definition. Entropy is really the number of ways you can arrange things. Okay? It's really, entropy came out of statistics. Okay? Entropy came out of statistics. At the time, looking at entropy was called statistical mechanics. So the letter for entropy is S, capital S. That's where they got it from. And because statistics is going to be how you calculate how many ways things can be arranged. Okay? And I said disorder was high entropy. Why is disorder high entropy if entropy's the ways it can be arranged? Okay? Well, because there's a lot more ways to make something messy than there are ways to make it neat. So if entropy is the number of ways you can arrange it, messier has more ways to be arranged. Neat has fewer ways. Okay? And the first law of thermodynamics says the energy of the universe is constant. We already talked about this one. This was our energy one. This is about energy. If the energy of the universe is constant, then energy can't be created or destroyed. So the first law of thermodynamics is the law of conservation of energy. It's the same law. So we've already used the first law. The second law is, second law of thermodynamics is the entropy of the universe increases in any change. So we're back to that whole universe situation. The entropy of the universe has to increase in any change. So anything that's going to happen has to make the entropy of the universe increase. The universe gets messy every time you do something. While we can't look at the whole universe at once, we can look at smaller systems and see that they tend to do this. The entropy tends to increase. If you drop a box of marbles, they hit the ground and bounce randomly. There's a chance that they could all end up in a straight line. Is that what you expect to see when you drop a box of marbles? Why not? You always see them, they spread. You can't predict ahead of time which way they go because they spread themselves out randomly. There's more ways to arrange them all over the floor than there are ways to arrange them in a straight line. So the straight line is low entropy, all over the floor is high entropy. Okay. Or just watch your room for a week. Don't clean it up. Just watch what happens to it. It gets dusty, it gets dirty. Look at my table, my demo desk. The entropy increases on my demo desk every day. There's more ways to arrange these piles that are messy than there are ways to make it neat. So things tend to get messier. We don't expect them to drop something and have it form a nice picture. Okay? So locally it tends to happen, we see that, but whatever it has to happen for the whole universe. The universe as a whole. Okay, one of the things that affect entropy is the state of matter. The entropy of a solid is low because a solid is regular, repeating, three-dimensional arrangement. There's not a lot of ways to make a regular, repeating, three-dimensional arrangement, so solids have low entropy. In liquids, the pieces can be anywhere in the liquid and they move past each other. More ways to arrange it if you can move the pieces all over the place. The entropy of a liquid is higher. Entropy of a gas, well, if I take that liquid and turn it into a gas, I move those particles 1,000 times away from each other. That's mostly empty space, so they got 1,000 times the space to be in. And if I had a room 1,000 times bigger, I could make it 1,000 times messier, right? So that's why it's not just, it's much greater than. Gases have high entropy, liquids much lower, solids a little bit lower than the liquids. So that's, so two alligators' mouths means much greater than, right? So the solid is orderly, regular, repeating, three-dimensional arrangement. A liquid has molecules next to each other, but it isn't orderly. In a gas, the molecules are moving all over the place, so they can be many, many more ways of arranging it in 1,000 times the box. Now, if you think about the outside limit of what we said, the entropy of the universe increases in any change. that means eventually the universe will all be entropy. It'll all be randomness. It'll all be disorder. That's how I think the universe is going to end. Heat death of the universe. Everything's random. And so, entropy increases when we do the following things, and decreases when we do the opposite. Okay? Well, at those phases, if I start off with a solid and I make gases, I've gone from low entropy to high entropy. If I start off with a liquid, or a solid and turn it into a liquid, I've gone from low entropy to slightly higher entropy. Liquid to gas, the entropy is going to increase. This is just another way of saying those alligator mouths we had on the last slide. This is the same as the alligator mouse on the other one. If I go from low entropy to solid, the other two are going to be higher. That's going to be an increase. Okay. The more pieces I have, the more ways I can arrange them. So if I've got one substance and I make it into two, there's more ways to arrange two pieces than one piece. So if I start off with one reactant and make two products, I can expect an increase of entropy. If I take two reactants and make one product, I'm going to expect the entropy to decrease because there's fewer ways to arrange one piece than two pieces. And I work pretty hard to say it as ways to arrange because that, for me, that's easier to think about. I don't make as many mistakes when your book is going to say it looks like chaos, but that's what it looks like. That's not what it is. Ways of arranging. Okay. If I raise the temperature, entropy is going to be raised because random motion of the molecules means they can be in more places in the same amount of time. So I've got something moving slow versus something moving fast. There's more ways to arrange the fast one every second because it's moving faster. And entropy is going to be increase when you dissolve it. Because when you dissolve it, you take that nice crystal and spread it out through all that water. And you've got two pieces next to each other. The more pieces you have next to each other, the more ways there are to arrange them. So which of these explains why ice melts? Well, which one of those describes what happens when ice melts? Oh, when ice melts, you start off with a solid and end up with a liquid. Start off with solid, end up with a liquid. Entropy, the reason why ice melts is because the entropy of the liquid water is bigger than the entropy of the solid ice. And so it's endothermic, but it happens because of entropy. So if we really want to figure out whether it happens, we have to look at two numbers, the one for entropy and the one for enthalpy. So let's double check. Which of these is an entropy increase? Is that an entropy increase? Yes or no, and why? Tori? Yes, because of gas. That's one of the possible answers. Yes, because I went from a solid to a gas. Is there another reason why it's an entropy increase? Okay. Yeah, I had two pieces here. I've got 7 pieces there. So for both those reasons, this is a entropy increase. Is that an entropy increase? Okay. Okay, it's 3 pieces going to 2, so that's a decrease. Okay? And it's 3 gases going to 2 gases. That's a decrease. Okay? Does that make sense? So this is not going to increase for both reasons. Is that an entropy increase? They're both gases, but this has 2 pieces and that has 1, so it's a decrease. I went from 2 pieces to 1 piece. There's fewer ways to arrange 1 piece than 2 pieces. Okay? Is that an entropy increase? Okay. How many people say that this is an entropy increase? How many people say it's a decrease? How many people have no idea how to do this? Well, good, nobody raised their hand there. But it should be pretty straightforward. 1 and 1, so it's not a number of pieces, but liquid, gas. Gas is all spread out, more ways to arrange it. Yes, Tori. Increase because it's dissolving, so I had sugar and water separate. There's more ways to arrange it if I put the sugar and the water together, because they're next to something different.
Decrease because when it goes from liquid to the solid.
Yep, so what you have to do is translate that into what's going on. Water freezing is going liquid to solid, and solid is regular, repeating, 3-dimensional arrangements. Okay, when you draw a picture of a snowflake, it's always 6-sided. It's kind of regular repeating. There are fewer ways to make 6-sided pieces, right, than random pieces. Actually, we'll talk about entropy calculations tomorrow. So, entropy makes the world go round. So the actual reason why everything happens is actually the second law of thermodynamics. If we're going to predict what's going to happen, we got to look at the entropy not of that little system, but of the whole universe. So when that ice melts, it's increasing the entropy, right? But sometimes water freezes. That's a decrease in entropy. What makes the difference? We'll talk about that tomorrow.